let's see, so sigma. And so we've got this, this thing here. And it's pretty similar to what you did in, homework 1. The only difference is that those coupling from the leads to the device are different from the coupling in the leads. So, just to make sure, the surface green function of the leads, like G00, is the same one you had from homework 1. It's no different, and that was like, what was the surface green function of the leads? I think it was something like e to the IKA over T, something like that.
But in homework 1, we did not actually find any surface gain function. Solve it normally.
Can't remember what you had to do. You didn't need to get a self-energy, or what did we have to do in homework 1? Oh, well, I guess the solutions are down here. Driving the wave vector K. Yeah, I just wrote this down, I don't know. But, the form, okay, so the form of the self-energy that you need is you need the surface green function of those semi-infinite leads, which is something like this, what I wrote down. So that should be in, like, chapter 2, and the self-energy, say, from coupling to the left lead, is going to equal, what did we define these matrix elements to be? Like T left, G00, since the T's are real. So that's just, T left squared. And that's going to be the self-energy. And so the difference is that TL and TR are now different from T. Right, so this T is different from this T.
You cannot see them.
Oh, sorry. So the T's are, this T is the T from the semi-infinite leads. And this is the T that couples the lead to the device. That's the only difference. And don't take my word that this is correct. Check the signs and all that.
I'm sorry, is this for the current homework?
Yeah. Yeah, so we're looking at the very first 6A. Problem 6A. So you need to get sigma. Right, so sigma is going to have 2 parts. So it'll be the sigma due to cup.
Can't you define the sigma as like T minus mod absolute of T left e to the power IK?
Say that again?
So how do we define sigma? Sigma is T e to the power IKA, right?
Not anymore. You define it as T01, G00. So in this, right, it's T10, G00, T. That's what it is, always. That form is always correct. And you're going to have another one coupling. So this is due to coupling to the left lead. And this, due to coupling to the right lead, is going to be your TR, G, I guess, in my numbering system. I don't know how I do. TRG, I'm just calling this node 1, so G11, that's the surface green function of the right lead, TR. And then I'm not even numbering my device, so my device green function will just be calling GRR. And that the R stands for your resonant level, because this is a simple model for a resonant tunneling diode, or any resonant state coupled to 2 leads. So that's the form of your two self-energies. So the total self-energy is,
I can see.
sorry,
I'm just not understanding, like, how is this problem different from our last homework? Because
the only difference is the coupling from the leads to the device is different from the coupling in the leads itself. So these T's are basically the bandwidth of your semi-infinite leads. These T's are much, much less. And that's why it's a resonant level. So somewhere I say that. So,
So you want us to solve this thing using surface green function, not the way we solved it in homework 1.
you really don't have a choice. Well, you probably have a choice, but this is definitely the way you want to solve it. Right? So this is the surface green function, and all you do is multiply by t left squared and t right squared. The surface green function is a property solely of the leads, and the leads haven't changed from what you did in homework 1. The leads have not changed. It's just the coupling of the leads to the device, and the device and that one node in the center has changed. And so I guess sigma is going to be what? What do you want, this?
yeah.
But I wanted to comment on this for a moment. So the sigma, I mean, this sigma is of course, just like last time, it's the sum of the two, right? So sigma is sigma left plus sigma right. Okay, so the sigma is, the only difference from what you did last time is that, I mean, I think it's going to come down, I think, I'm pretty sure that this expression up here, please check it, is correct for the surface green function. And that K would be the K either for your left lead or your right lead. And so, before, when we converted to a self-energy, the T's you had, so before, when everything was the same and uniform, you had sigma was T squared e to the I Ka over T, and so the T's canceled, and you ended up with, am I doing this right? You ended up with T e to the Ika, or plus or minus T e to the Ika, something like that. Now the T's don't cancel because they're different, right? So that was Zen. Now we have this TL squared, which is much less than T e to the Ika. So you're not going to be able to get as nice of an expression as you're not going to be able to use your dispersion relation to simplify it into something very cute. And you check your sign. So the sign, I'm not sure about whether it's plus or minus here. Make sure you get the signs right. And one good way that I remember to check my signs, sort of like checking units, is that the form, when you write this out as E minus H minus sigma, right? This is the form of your green function. And if you write the sigma out as real and imaginary parts, the sign of the imaginary part has to be like this. E minus H. So we would have some real part plus I gamma over 2. So the sign of the imaginary part, when you write it like this, has got to be positive if you want a retarded green function. And so you can look at this expression that we have for, here, and now we can expand that out. So let's see. That means this is minus sigma. So it means that sigma, the form of sigma, has to be little sigma minus I gamma over 2, right? The imaginary term has to be negative. And so if I look at this, the imaginary term is I sine Ka. I sine Ka. What is that? TL squared is positive. T is negative, right? Or is T positive or negative? How do we write this darn thing? I guess all the T's have got to be negative.
Over real and negative here.
Oh, they're less than 0. So I guess we're good. Problem is Ka can go out, the maximum value of Ka can be like, oh, pi. It goes from 0 to pi. So the sign will always stay positive. So this will always stay negative. Yeah. Okay. So I think we have the sign of this is correct. You got to recall T is negative. Okay, so that's the difference between what you're doing this time. Well, the first difference to be aware of. Okay, so the next is, so let's see, write down the real imaginary terms, then just write down what this real part is when your energy, when everything's aligned, so your resonant level is the same as, this is like the middle of the band of your leads, right? When E equals epsilon is the middle of the band in this for the leads. Right, the band goes from like epsilon minus 2t to epsilon plus 2t. Well, these are kind of redundant questions. Just looking at the sign of this real part, the energy what they call the energy renormalization due to the coupling to the leads. Okay, this is a really important question here. This one, or something that has a lot of significance. So, the most important thing. So for this question, this is the most important thing, that you're setting TL equal to TR. So it's called what's called symmetric coupling to the leads. The coupling to the left and the right of your resonant level is the same. Just defining this renormalized site energy. So if this renormalized site energy lies anywhere within the band of states of your leads, this epsilon plus or minus 2t of the leads, or the bandwidth of the leads, the maximum value of the transmission is always 1, irrespective of whatever value. These have to be the same value, that's important, but no matter how big or small they are, the maximum transmission is always 1 through that resonant level. That resonant level lies anywhere in the band. So this has caused a lot of confusion back in the late 80s, because so what we're looking at is we have this band of states coming in from our leads, right? Some band of states. We've got our resonant level here, and there's some coupling that couples, there's some coupling that couples the resonant level to the leads. And if there were no coupling, that resonant level would be a truly bound state, and just a discrete, spectrum would be a delta function in energy. It would have no width. But because there's some finite coupling, just in there, as a discussion we went through with our self-energies and all, there's a finite lifetime, right? If I put a particle on that resonant state, after some time it'll disappear into the leads. All right? That finite lifetime in time translates into a finite width in energy. And that width is h bar over tau, which is our gamma from our self-energy. So gamma is -2 imaginary sigma. That's your, what they, just like in an optical cavity, this is your full width at half maximum of this resonant. Just like an optical line width of a laser. And it's pretty much Lorentzian. And so this is both what, if you were to plot the spectral function, A of E of this resonant level, -2 imaginary. If you were to plot that, it would look like this Lorentzian, and it's also your transmission coefficient, which is, in this case, it's just going to be gamma left, gamma right, so we're set as symmetric, so it's gamma squared, right? Because gamma left and gamma right are the same, and G squared. So magnitude of G on that one site, magnitude squared. And so, you know, it becomes very simple as we look down here. So the total current that can pass through this resonant state is given by this. So in this situation, say that all these, you know, all these states are filled, so they're all like coming, you know, injecting like this, and assume that all these are empty, so that, you know, you can get your, all these states on the left are filled and injecting towards your resonant level, and all the states on the right side are empty, so everything can go through. So when you think of, you know, T times F left minus F right, you assume F right is 0, F left is 1, and then you integrate, right? You integrate over all E, dE over 2 pi, and your whatever factor goes out front is 2E, what is it? E over H bar, E over H bar, and that's the maximum current that can possibly flow through that level. Right? Set F left equal to 1, Fr equal to 0, and then you just integrate the transmission coefficient, and that's the maximum current that can possibly flow through that level. Well, doing that integral using the actual self-energies and actual energy-dependent gammas is too hard. So what people do is they use an approximation for the self-energies, and they just say, okay, sigma left, due to the left lead, is just minus I gamma left over 2, and sigma right, due to coupling to the right lead, is minus I gamma right over 2, where the gammas are just some number. And then everything becomes very easy, and you can do all your integrals and everything analytically. And once we do that, and we set the gammas equal, then we can, you know, explicitly look at these expressions. So, you know, first of all, your G of your resonant level is just going to be 1 over E minus the resonant level energy. And notice in this approximation, I just totally ignored any real part. Okay, I just kept the imaginary part. So this will just become plus I, and I'm going to set the gammas equal, so I just get gamma. Gamma left plus, so that's, how do I say it? Yeah, that's just gamma, right? Either gamma left or gamma right, but they're the same thing. I don't know if that's the best way to write. It gets, let me think for a second. So gamma equal, gamma left plus gamma right. Let me keep it like this. I times gamma left plus gamma right over 2. Right? That would be the general form in this approximate, if you approximate the self-energies like this. And so now we can explicitly take -2 imaginary, right? So if I take -2 imaginary, A of E is going to equal gamma left plus gamma right over E minus epsilon R squared plus this square, gamma left plus gamma right squared over 4. And similarly, you can write down your transmission too, because g squared has the same denominator. So your transmission is just, gamma left, gamma right over E minus epsilon r squared plus this, the denominator is the same as before, gamma left, gamma left plus gamma right over 2 quantity squared. So same denominator for both. The only difference is the numerator. So the denominator is what determines the full width half maximum. So you can immediately see by looking at the denominator that this full width half maximum gamma is gamma left plus gamma right. That's your full width half maximum. And if you think of adding rates, it's just the rate of leaking out to the left lead plus the rate of leaking out to the right lead. Right? You add rates, and that's all it is. Adding the total rate, which you'd leak out either to the left lead or the right lead. And so once you make this approximation for the self-energies, then you can integrate T exactly. Right? You could do this either by contour integration, which is, for me, simpler, or you can remember that with some substitution, I think it becomes an arctan function. But you can do this integral, and it just, so the problem says use this form of sigma to explicitly evaluate the maximum current that can flow. So basically, you're just integrating this expression for T, and getting something that's going to be the only thing that's going to be left is gamma L and gamma R in the final expression for the maximum current that can flow, I guess, times an E over H bar. You don't have to make this approximation to do this. You can let these become, leave these as everything as a function of energy to show this, that when these couplings are symmetric, then you also, I guess you need to also assume here that there's no bias across. So everything is symmetric between the left and the right, so that your surface green functions are the same, your couplings are the same, TL and TR, and then the maximum transmission is always 1, no matter how weak or how strong the coupling. What the coupling determines is how wide your resonance is. You can already see that because that's gamma L. So it determines the width of the resonance. As I make the coupling weaker, right, the resonance eventually has to go back to a true delta function as that coupling goes to 0. And so the coupling determines the width of the resonance. And you'll see when you look at this that the height is always going to be, for symmetric coupling, 1.0 for the transmission. And so if the height is fixed and the width is changing, it means the area is changing. And that area is what's giving you the maximum current. So, right, if you want to engineer the current, then you're looking at engineering the width. The width is what's changing, at least for symmetric coupling. Okay, I guess we already did F. So this is often when you set these self-energies just to be a constant. It's called the wideband approximation, because there's no energy dependence to these self-energies. So F is what we just did, right? This is a full width at half maximum. This is F. And then it's just playing around with your expression. So again, using this approximation for your sigmas for all this stuff, fixing gamma R and saying what gamma L will maximize the transmission coefficient and what gamma L maximizes the current, the maximum current that can flow. And finally, in the last one, if this resonant energy is very narrow and sharp, then when you want to calculate the either the current or the electron density. I mean, if you're calculating current, you have this E over h bar integral dE over 2 pi T of E, F left of E minus mu left minus F of E minus mu right. Now, at room temperature, the F is only varying on the order of 26 millivolts, right? That's kind of the scale of which F varies over. But if you have a very narrow resonance, say 1 millivolt, then this kind of looks like a delta function, peaked at its center resonant energy, right? So if it's very narrow, then you just approximate it as a delta function, and you end up with E over h bar. Sorry. E over h bar times, if it's a delta function, I guess E over 2 pi h bar with just E over h times F of, you just replace E with the resonant energy. Right? If it's a very narrow resonance compared to KT. And so the final problem is doing the same trick with the electron density. So we want to find out the electron number. What is the average number of electrons on this resonant level? So for problem H, so the average number of electrons. So first we need the expression for the average number of electrons. So we had that N is, say on site R, which is our device. What did we have? We had something like integral dE over 2 pi. This is the only way I can ever remember it. A left, times F left plus A right times, F right. And so A left is our gamma left. It's just gamma left, G, R, R, gamma left, right? And this is just gamma right, G, R, R, gamma right. Well, and these are all just numbers, so it's like, gamma left squared, G, R. R and gamma right squared, GRR. Is that right? Did I get? Oh, I got it backwards, don't I? GR gamma GA. Oh, I got it backwards. Sorry. It's GRR gamma left GRR. If these were matrices, we would say dagger, but these are all scalars. So it's just GRR magnitude squared gamma left. That's our left injected spectral function, right? And our right injected spectral function is just GRR squared gamma right, right? And well, we know GRR is just this. We already, somewhere, here it is, right? Here's GRR. We've already done GRR squared to get T, right? GRR squared it's just the denominator squared, magnitude squared, right? Times gamma left or gamma right. And the denominator is the same in both of these terms. So again, we're just ending up with, right, the denominator due to these A's is the same. It's just coming from our G squared term, right? Denominator. So it's all over a common denominator of this, E minus epsilon R magnitude squared plus the thing coming out of the imaginary, gamma L plus gamma R over 2 quantity squared. Right? That's the denominator, the common denominator. And then in the numerator, I guess you're just going to have like, gamma L times F of E minus mu L plus gamma R times F of E minus mu R. And then I'm saying you approximate, you pull the, you can pull the F's outside the integral by just evaluating them at the resonant energy, assuming this is a strongly peaked, integrand due to the denominator. You pull them outside the integral, and then you've just got the same integral you've just done, right? Break it up into two parts. You got one due to the left, one due to the right. You add them all together, and you'll get your expression for the average number of electrons on that resonant site. And when you look at that final expression, that you get, it's going to look, it turns out to be exactly what you get from just solving a rate equation. If you had, so you've got the central site, and you've got F left, gamma left. So this would be the rate, sorry, going onto your device, F right, gamma right, and then we've got to do like, so that would be what's going in, and then you got to do what's coming out. So what would be coming out? So what's coming out would be F on the device, F on the device, gamma left, the rate is the same, times 1 minus F left. And this is, again, F on the device, gamma right, 1 minus F right. And so maybe we need to, what's going in has got to be, these should all cancel if we do everything right. Since everything is elastic, I think we can just ignore these two right from the beginning. 1 minus F on the device. All those 1 minus F terms should cancel. If I just ignore all the 1 minus F's, let me just see what I get. So I would get that what's going in has got to equal what's coming out, right? So FL gamma L plus FR gamma R has got to equal FD times gamma L plus gamma R, right? It's setting the inflow equal to the outflow. And so FD is equal to gamma L FL plus gamma R FR over gamma L plus gamma R. And I believe that is the answer you get from integrating out the NEGF equations. So to the extent that that line width just looks like a single level, it comes down to a classical rate equation. Physics is no different than a classical rate equation. And you can go through and look at different limits, and this makes perfect sense. I mean, if it's like, if gamma, if the rate is out to the right side is really small and the rate in from the left side is really big, then you can ignore the rate, you can ignore gamma R, and you get that the occupation is just given by the Fermi factor of the left lead, because you get FL gamma L over gamma L. And that makes sense, right? If you reduce the coupling to the right, it's just going to be equilibrated with the left. And in terms of an actual device, when people were building these, what that means is you have a structure like this. You have a skinny barrier and a fat barrier, and then the occupation of this level here, if you have different doping or something or other by. It's going to be determined by, this coupling is very strong. It's going to be equilibrated with the left lead.
Why do I need asymmetric behavior?
Oh, this is like, this represents your gamma right and your gamma left. What we were just saying, I said if you make gamma right, the rate much smaller than gamma left, and that's the way you'd actually do it.
But from my device, from my application perspective, like, is it like useful?
Depends what you want to do. If you want to have a lot of charge in the well, then that's the way you do it. So, for some experiments, people wanted to get a lot of charge built up in the well. So under bias, when you apply a bias to this thing, you have this big fat barrier. And as you apply a bias, you get a lot of charge built up in the well. And so as you get this charge built up, your curve goes out and out and out, and finally, eventually, with enough bias, it discharges, and you get your normal curve like this. And then when you sweep it back, you get this bistable region. People were really excited about that for a while due to this charging and discharging of the well. Because now when you sweep it back, it's empty. And so the potential is going to be different on the back sweep than on the forward sweep. Because on the forward sweep, it's filled. And on the back sweep, it's empty. So the potential profile is different. It gives you this bistable curve. That was a phys-rev letter back around 87 when they saw that experimentally. Caused a lot of excitement.
Well, for my forward sweep, why should current suddenly decrease?
I'm sorry, what?
In my forward sweep, why should my current suddenly fall back?
You mean the NDR part here?
Yeah.
Well, as you apply a bias more and more, it's kind of hard to draw this. Eventually, you pull this, all your states are up here. When you pull this level down below your injecting window of states, then you go off resonance. The only way you can now go in is by emitting a phonon. So when you're up here, you can go right through, and you're resonant. Once you pull this level below those injecting states, you're off resonant, and you don't have any direct channel to go through that level anymore. The only way you can go through is by transferring momentum with a phonon. So when you pull that resonant level down below the conduction band of the source, that's when you go into the NDR region.
But in my backward sweep, that part, how are they escaping or discharging? Because
once you pull it down below the resonant level, then there's two things happening. One is you can think of the gamma. These gammas aren't changing too much, so keep the gammas fixed. But suddenly, at this point, your effective F here becomes like F left becomes like 0, because that's one way to think about it. Or gamma, if you like, gamma, because there's no states here, your surface green function is 0. It's probably more appropriate to think of as the gamma left suddenly goes to 0, because there aren't any states there to inject. And so suddenly this goes, and so if this goes to 0, the only thing left is gamma right, and so it becomes equilibrated with the right lead. It just empties out because there's nothing filling it anymore effectively. So once it gets pulled down, then it empties out. And if you go back and think about Poisson's equation says that, if I can remember it, grad squared phi is negative rho over epsilon, I think. And so in 1D, that's just d squared dx squared of phi is negative of the charge. So if it's filled with electrons, and if the charge is negative, I'm filling it with electrons, and d squared dx squared is positive. D squared, it means the potential phi, the curvature has okay, so phi, it means that in the resonant well region, positive curvature means it's going like this for my potential, right? And so for my energy, it means the conduction band edge is doing this in the well when it's full of charge. You got to flip it over to go from potential to energy, right? Right? So it means that when there's charge buildup in the well, the bands here are actually pushing up like this. And when they're pushing up, it means I got to apply more voltage to pull this resonant level down below the injecting states. It's fighting against the voltage, the charge buildup. Once it discharges, there's no charge, then suddenly the band snaps back to this state, and that's why I got to like bring the voltage back further before I can start filling it. Right, so when it's filled, the potential is pushing the bands up here, which pushes the resonant level higher. So it takes more voltage to pull it down below the band edge of the source. Clear?
Is that like here we are seeing that the NDR arises because there is a resonant level, and after some time my injecting states are above the resonant level, right?
Yeah.
But the paper Masul in the graphene bilayer paper there
Right.
was NDR. Was that for like similar effect?
No, that's just okay. Now we're getting into the transverse momentum. Similar in the fact that for a planar device, this is due to a mismatch in transverse momentum because this is really the bottom of a subband, but I really didn't want to get into that. So if you ignore the transverse, like these are made in a 2D sheet structure, so this resonant level is really the bottom of a subband in the XY out of the plane page. But if we think of a truly just 1D system, this is just a single level with then this is just a matter of energy conservation, right? These guys they're at the wrong energy. The only way they can get down to this energy is by emitting a phonon. What he was doing was a momentum mismatch. This is just a quantum well. He had two rotated things of graphene, and that had to do with momentum mismatch.
And why? My injection state has to emit a photon and come down to the resonant level. Cannot some sort of tunneling take place?
Yeah, it can, but it's off resonance, so it's much, much less. We just looked. We know what the transmission looks like, and we just explicitly calculated it. So if I have this situation and I'm injecting up here, and my resonant level is down here, we know the transverse energy spectrum is Lorentzian. So you're just integrating the tail of the Lorentzian, right? Because you can only integrate from like here on up, and you just get the tail of the Lorentzian in your integral. And the last problem is just completely different, just showing that this eigenfunction expansion that we did satisfies what it needs to satisfy to be a green function, which is just straightforward. You just plug in the eigenfunction expansion and show that you do indeed get the identity. That's it. Problem 6 and 7. There are a lot of parts to 6. And a lot of insight into this basic, simple model for the RTD, but has a lot of the basic physics of an RTD or any resonant level coupled to two leads.
Is the band structure would still be cosine band
For the leads,
for the device?
the device is one.
Yeah, on energy.
It's just one site, one energy, yeah. One level. That's your device. So it's one energy level weakly coupled to two leads, and these leads are a band of states. Later, when we do the recursive green function algorithm, we'll extend this a little bit and then add, say, another level here. Oh, I guess I can't write. Oh, here I go. Another level here and add some coupling and see what happens when you do something like that. Or I think maybe it's set up so you just have your ideal, your ideal wire, and then you have one weakly coupled level up here, some weak coupling, TR, and just your ideal chain down here. And that's another classic problem of a bound state weakly coupled to the continuum. And that gives you, I have to double check, but that will give you a Fano resonance. Classic Fano, looks like. If you plot the resonant line shape, it does something like this instead of the Lorentzian. That comes from destructive and destructive interference when you have two paths. Like you can just go straight through, or you can go up and like that. And you can get constructive and destructive interference. But we'll do that after we do the recursive green function algorithm.